73 seconds into flight, the vehicle disappears into a cloud of smoke and fire. The telemetry screens freeze. The chatter and Houston's mission control stops. Thousands of data points drop to zero in a single instant. The immediate reaction framed this as the inherent danger of touching the edge of space. It was widely perceived as the terrible, unpredictable cost of exploration. This failure began on the ground inside conference rooms, where specific engineering warnings were debated and eventually authorized as acceptable risks. By 1986, the Space Shuttle program was marketed as a reliable routine commute to low Earth orbit. The 7-person crew reflected that promise. Among them was Krista McAuliffe, a high school social studies teacher. Her inclusion sent a deliberate message. Space travel was safe enough for everyday citizens. That promise of routine access required a rigid launch schedule. Delays were costly and politically embarrassing. The pressure to keep flying built a heavy momentum within the agency's management. Selling spaceflight as a predictable commodity created a dangerous friction with reality. It masked the fact that they were still operating highly experimental, volatile rockets. The night before the January launch, a severe cold front swept across Cape Canaveral. Temperatures dropped well below freezing, encasing the launch pad and the vehicle in layers of ice. Inside a late-night teleconference, engineers from Morton Thiokol, the contractor responsible for the solid rocket boosters, sounded an alarm. They argued the cold weather would compromise the rubber seals inside the rocket joints. This chart shows the gap between testing parameters and reality. The solid rocket boosters had never been tested below 53 degrees Fahrenheit. That night, the temperature at the pad plunged to 18 degrees. The components at risk were the O-rings. During ignition, the extreme pressure of the rocket forces the metal casing to bend outward. To contain the burning fuel, these rubber rings must instantly expand to fill the widening gap. At 18 degrees, rubber loses elasticity. The hardware was scheduled to perform in a condition explicitly outside its physical design limits. The engineers recommended delaying the launch until temperatures rose. NASA management pushed back, facing a mounting backlog of missions and intense media scrutiny. They challenged the engineers' data. A critical procedural shift occurred during the debate. Instead of requiring the contractor to prove the launch was safe, NASA management demanded they prove it would fail. The agency had previously observed minor damage to these O-rings on past flights and survived. This created a culture of normalized deviance where accepting small, unpunished risks became the standard way of operating. At zero, the solid rocket boosters ignite. Inside the lower right booster joint, the frozen O-ring is too stiff. It fails to expand in time to seal the gap against the internal pressure. Searing hot gases escape through the joint. Cameras capture a brief puff of dark smoke near the base of the rocket as the material burns away. This graph tracks the shuttle's ascent toward max Q, the period of maximum aerodynamic pressure. As the vehicle accelerates through the lower atmosphere, the physical stress on the compromised right booster intensifies. The escaping plume of fire cuts directly into the main external fuel tank. At 73 seconds into the flight, the structural integrity of the tank gives way under the aerodynamic load. The laws of physics finalize the vehicle's fate at the pad, rendering management's flight schedules irrelevant the moment the countdown hit zero. In the aftermath, the Rogers Commission was formed to investigate. The public and Congress demanded a clear explanation of how the space program had failed. Among the commissioners was Nobel laureate physicist Richard Feynman. As the hearings progressed, he grew increasingly frustrated by the agency's reliance on complex bureaucratic language to obscure the mechanical truth. During a televised session, Feynman brought a piece of the O-ring material, a small key clamp, and a glass of ice water. He compressed the rubber, submerged it, and then released the clamp. Holding the still compressed rubber, he noted, "I discovered that when you put some pressure on it for a while and then undo it, it doesn't stretch back. It stays the same dimension. There's no resilience in this particular material when it's at a temperature of 32 degrees. That single physical demonstration bypassed weeks of administrative testimony. It stripped away the institutional defences and laid bare the exact mechanical cause of the disaster. The loss of the 7 astronauts forced a national reckoning. Their deaths were the result of decisions that compromised safety for scheduling. The investigation forced the aerospace industry to restructure its communication channels, ensuring that raw engineering data could no longer be silenced by management directives. Human bureaucracy operates on compromised deadlines and public relations. Natural laws do not negotiate. A functional engineering culture relies on the moral courage to stop the countdown when the data demands it. Because, as Feynman concluded in his personal report, nature cannot be fooled.